Welcome to Upsc Study Academy, empowering aspirants and shaping futures. Today we are covering the topic, waves, which is a part of the science and technology paper. In this video, we will be covering the following topics. What are waves? The different types of waves, characteristics of waves, properties of waves, and real-life examples of the same. The first heading, waves. What are waves? A wave is a disturbance in a medium. It transports energy without the transport of matter. It is a fluctuating oscillation that transports through a medium. It is produced by the temporary displacement of a particle belonging to a medium. Waves travel through both light and sound and are propagated into different types. Topic 2. What are the types of waves? Waves are broadly classified into two: the mechanical waves and electromagnetic waves. The mechanical wave is further divided into two: transverse waves and longitudinal waves. The electromagnetic wave is divided into 7 major types. They are radio waves, microwave, infrared radiation, visible light, gamma rays, ultraviolet radiation, and X-ray. Mechanical waves. Mechanical wave requires a medium to travel. They cannot travel through vacuum. They propagate by causing the particles of the medium to vibrate. Waves produced by oscillation in water are example of mechanical wave. Longitudinal waves. In longitudinal waves, the motion of the vibrating particle is along the direction of motion of the wave. Sound waves and seismic wave are great examples. This is a representation of the longitudinal wave, which shows the amplitude, the expansion, the direction, the wavelength, and the compression of the wave. The transverse waves. In the transverse waves, the particles of the medium move perpendicular to the direction of the propagation of the wave. Waves formed in the surface of water and strings are common examples. This is a pictorial representation that shows the crest, the wavelength, the amplitude, the equilibrium, and the trough of the transverse wave. Longitudinal wave versus transverse wave. The difference. In transverse waves, the particles of the medium oscillate perpendicular to the direction of propagation of the wave, creating crests and trough. In longitudinal waves, the particles oscillate parallel to the direction of propagation of waves, creating compression and refractions. Transverse waves exhibit a side-to-side or up-and-down motion, creating a wave pattern resembling ripples on a water surface. Longitudinal waves, on the other hand, cause particles to move back and forth in the same direction as the waves, forming regions of compression and rarefaction along the wave. Transverse waves require a medium that can support shear stress, such as solids and fluids, but they cannot propagate through a vacuum. Whereas longitudinal waves propagate through solids, liquids, and gases, as they rely on the compression and rarefaction of the medium's particles. Electromagnetic waves. The electromagnetic waves are oscillating electric and magnetic fields that travel through space at the speed of light. They don't require a medium and can propagate through a vacuum. Electromagnetic waves can span a wide range of frequencies, from radio waves with long wavelengths to gamma rays with short wavelengths. They exhibit wave-particle duality, behaving both as waves and as particles of light called the photons. Electromagnetic waves are responsible for various phenomena, including light, heat, and radiation. They can be produced by acceleration of electric charges or changes in magnetic fields. Radio waves. Radio waves are a type of electromagnetic radiation with long wavelengths and low frequencies. They are used extensively in communication, broadcasting, and radar systems. They can easily penetrate through obstacles such as buildings and clouds, making them suitable for long-distance communication. Radio waves are a part of the electromagnetic spectrum and have wavelengths ranging from a few millimeters to hundreds of kilometers. Microwaves. Microwaves are characterized by long wavelengths and low frequencies. They are commonly used for wireless communication, including AM and FM radio broadcasts. Radio waves can travel long distances and penetrate through obstacles like buildings and clouds with ease. Different frequencies of radio waves are allocated for various applications by regulatory agencies like the FCC. Despite being low in energy, radio waves are essential for modern telecommunications, enabling global connectivity and information dissemination. Understanding radio waves is fundamental for designing and optimizing wireless communication systems. Infrared radiation. Infrared radiation is a type of electromagnetic radiation with longer wavelengths than visible light, but shorter than microwaves. It's commonly associated with heat and thermal energy. It's utilized in various applications including thermal imaging, night vision technology, and remote controls. Infrared radiation is absorbed and emitted by molecules, leading to its role in greenhouse gas effects and climate regulation. It's used in industrial processes like heating and drying, as well as in medical applications for therapy and diagnosis. Infrared photography captures images by detecting infrared radiation, revealing temperature variations in objects. X-rays. They are a form of high-energy electromagnetic radiation with short wavelengths, shorter than ultraviolet light and longer than gamma rays. They have the ability to penetrate most objects, including soft tissues, but are absorbed by denser materials like bone. X-rays are commonly used in medical imaging to visualize the internal structures of the body, aiding in diagnosis and treatment. They are also used in security screening, materials analysis, and industrial inspection. X-rays were discovered by Wilhelm Conrad Röntgen in 1895 and have since become an indispensable tool in various fields, revolutionizing medicine and science. Visible light. Visible light is a narrow portion of the electromagnetic spectrum, perceived by the human eye as various colors. It ranges from approximately 400 to 700 nanometers in wavelength. Each color corresponds to a different wavelength, with red having the longest and violet the shortest. Visible light enables us to see objects and our surroundings, crucial for navigation and perception. It behaves both as a wave and a particle called a photon. Visible light is emitted by the sun and other sources of illumination and can be reflected, refracted, or absorbed by materials. Ultraviolet rays. Ultraviolet radiation is electromagnetic radiation with shorter wavelengths and higher frequencies than visible light. UV radiation is invisible to the human eye, but can cause sunburn, skin damage, and even skin cancer with prolonged exposure. It is emitted by the sun and can also be produced artificially in devices like UV lamps. UV radiation is categorized into 3 types based on wavelength: the UVA, the UVB, and the UVC. While UVA and UVB reach the Earth's surface, UVC is mostly absorbed by the ozone layer. Gamma rays. Gamma rays are the highest energy electromagnetic waves with the shortest wavelengths in the electromagnetic spectrum. They are produced by radioactive decay, nuclear reactions, and high-energy astrophysical processes like supernovae and black hole accretion disks. Gamma rays are highly penetrating and can travel long distances through various materials, posing health risks to living organisms. Despite their potential danger, gamma rays have valuable applications in medical imaging, cancer treatment, and radiotherapy. Oscillation versus waves. The difference. Oscillation involves repetitive back-and-forth motion around a central point or equilibrium position. This motion can occur in various forms, such as the swinging of a pendulum or the vibrating of a guitar string. Waves, on the other hand, involve the transfer of energy through a medium or space without the net transfer of matter. Waves propagate outward from a source, carrying energy but not necessarily material particles with them. Oscillation typically occurs within a localized region, with the oscillating object moving back and forth within that space. Waves propagate through a medium or space, spreading outwards from the source of disturbance. As waves travel, they transfer energy from one point to another. Energy is continually exchanged between kinetic energy. Energy is transferred from one location to another without necessarily involving the movement of matter. Going to topic 3. The properties of waves. The properties of waves are broadly divided into reflection, refraction, dispersion, diffraction, and polarization. Reflection of waves is calculated by the angle of incidence, that is the angle between the incident wave and the normal to the surface, which is equal to the angle of reflection, which is the angle between the reflected wave and the normal. Refraction of waves is the bending of waves when they pass from one medium to another with different densities, causing a change in their speed and direction caused by a change in wave velocity. Diffraction of the waves is the bending of waves around obstacles or through narrow openings. The degree of diffraction depends on the size of the obstacle or opening relative to the wavelength of the wave. Dispersion of waves is the separation of waves into different colors or frequencies as they pass through a medium. The wave travel at different speeds, causing them to spread out and form a spectrum. Polarization is the orientation of the oscillations of waves in a particular direction. Waves vibrate in a specific plane, perpendicular to the direction of propagation. This pictorial representation shows the behavior of waves under the reflection, absorption, and refraction stages. And this shows the behavior of waves in the transmission, diffraction, and scattering stages. Moving to the characteristics of waves. Characteristics of waves can be understood by studying the frequency, amplitude, wavelength, and time of a particular propagation. Frequency, which is calculated in hertz, is the number of complete oscillations or cycles of a wave that occur in 1 second. It's measured in hertz. Frequency and wavelength are inversely proportional. As frequency increases, wavelength decreases, and vice versa. Amplitude is the maximum displacement of a wave from its equilibrium position. For a transverse wave, it's the maximum displacement from the equilibrium line, while for a longitudinal wave, it's the maximum compression or rarefaction. Wavelength is the distance between two consecutive points in a wave that are in phase, such as two crests or two troughs for a transverse wave, or two compressions or rarefactions for a longitudinal wave. Time period is the time taken for one complete oscillation or cycle of a wave. It's the reciprocal of frequency and is measured in seconds. Moving on to the final topic. Examples and real-life application of the different types of waves. Some of the examples of transverse waves are light waves, heat waves, water waves, radio waves, and seismic waves. The examples of longitudinal waves are the sound waves, P-type seismic waves, spring waves, vibrating drumhead, and spring coil waves. Real-life applications of electromagnetic waves. Radio waves are mainly used for communication, like the radio, TV broadcast, radars, cell phones. Microwaves are used in heating and cooking appliances and tools. They are also used in Wi-Fi networks and telephone circuits. Infrared waves are used in night vision equipments and various imaging cameras. They are also used for their high thermal effects. X-rays are mainly used in astronomy, medicine, radiation therapy, and security systems for their potential to pass through particles. Gamma rays are used for PET scans, cancer therapy, astronomy, and food sterilization. UV rays are used for water disinfection, manufacturing of fluorescent material, and checking of counterfeit currency. And that's all for this video. Thank you for watching Upsc Study Academy. Do like, share, comment, and subscribe. Do not forget to hit that bell icon.